Hello everyone, this video is going to cover three different systems for physics. The first will be static rotational equilibrium of a tilted bar. Then we'll cover two systems of simple harmonic motion for simple harmonic oscillators like the Spring-Mass system and the simple pendulum. First section we're going to be dealing with is the static rotational equilibrium of a tilted bar. And for this part, you're going to want to make sure that your calculators are set to degrees. Here we have a problem. We have a tilted bar. It's not completely horizontal, and we have a few forces, a few weights acting on the bar. The actual bar itself is 60 newtons, and there are two weights hanging on the bar as described, and one weight labeled A has a force of gravity of 50 newtons, while the other weight we don't actually know. We're going to try to figure that value out to see what that weight needs to be in order for this bar to be under static equilibrium, rotational static equilibrium. That is where all the torques add up to zero. And the information that we're giving is that this is a 60 Newton bar, so that would be its weight, and it has two hanging masses, A and B. If the bar is at static equilibrium, rotational static equilibrium, where the net torque is 0 Newton meters, let's determine the weight of B. And just to emphasize, weight is in newtons, it is a force, it is not equivalent to mass, which is in kilograms. Well, what we're first going to want to do is figure out all the forces that are at play on this bar. And for mass A, we know that we have a 50 Newton weight, and it is a force of gravity, which is always pointed straight down. And that's the same thing for B, where it will have some force of gravity that we do not know the magnitude of, but we know its direction is straight down. Because of the tilt of the bar, the angle between our force vector and our distance vector to the point of pivot or the point of rotation, well, we have two angles here. We have 30 degrees and 150 degrees. Those are complementary angles. That just means that adding those up, it gets you to a full 180 degrees. When it comes to sine, unlike with cosine, sine of complementary angles equals the same value. So here it doesn't matter for the bar if you use 30 degrees for force of gravity or use 150 degrees, essentially the smaller or larger angle. They'll both give you the same thing. One thing that we should note is we're assuming that the bar, which has its own weight of 60 newtons, we're assuming that that is a uniform mass bar, which means that its force of gravity is at the center of the bar. Since the bar is a total length of 20 meters, the bar's own weight is going to be pulling at the center of that bar, or essentially 10 meters from either end. Now if we calculate the torque of those three forces that are at work on our bar, torque of force A, that would be its force magnitude of 50 newtons. Its distance away from the point of rotation from that X in our diagram, well, if the entire bar is 20 meters in length, and essentially what we have here is 5 meters that we are not including and 3 meters that we are not including, the distance between force A to the point of rotation would be 20 minus 5 minus 3, or 12. And, well, once again, for sine, it doesn't matter if we use the smaller angle or the larger angle of 150 degrees. When it comes to sine of complementary angles, they both equal the same thing. So whether you have sine of 30 degrees or sine of 150 degrees, it doesn't matter. And then this positive 1 is because this downward force pulling this direction, where our point of rotation is over here, this would cause a counterclockwise torque, hence a positive 1 direction for torque. And multiplying all of these, we get positive 300 Newton meters of torque for force A. For the bar, our only other known force, its magnitude is 60 newtons, and its distance, excuse the correction there, for the torque of the bar's own weight of gravity, that would be the 60 newtons of force of the bar, And our distance between where that force is applied to the point of rotation, that is going to be 7 meters. So that's effectively this distance right here. And, well, again, you can use either the 30-degree tilt or the 150-degree tilt. Sine of either will give you the same value, which happens to be 1/2. And again, this will be a positive torque or a counterclockwise rotation. Hence, we have positive 1. And multiplying these across gets us positive 210 Newton meters of torque. And then our last torque, torque of B, we don't know its force. We don't know its weight. That's what we're trying to calculate. So initially, we'll just label it as force of B. What we do know is the distance between this force and our point of rotation. That is going to be this 3 meters right here. And we know the angle. Forces of gravity are always straight down, and if our bar is tilted 30 degrees or 150 degrees, whichever you want to look at it, you can use that angle in for sine. But one thing we need to know is that this force is pulling straight down, and the pivot point being here, this would cause clockwise rotation, hence the -1. And so 3 times 1/2 times -1 equals -1.5 times the force of B, Newton meters. Now, we are in static equilibrium for the rotational direction. That means that the net torque has to equal 0, and the net torque is our 3 individual torques, or however many torques that were involved in our problem. Torque of A, torque of the bar, and torque of B. All 3 of these have to add up to 0. Well, torque of A was 300 Newton meters, torque of the bar was 210, and torque of B was -1.5 times the force of B, hence why we have a negative sign here. And then all those have to equal 0. The only unknown is the force of B, so 300 plus 210 is 510. Adding, subtracting that to the other side is -510 Newton meters, dividing by -1.5 to get force of B by itself. The weight of object B is -510 Newton meters divided by -1.5 meters, which comes out to 340 newtons. Next sections, we're going to be covering 2 examples of simple harmonic motion. And for those 2 examples, essentially one is going to be a mass spring where we have a 3 kilogram mass on a spring, and that spring is given a displacement or an amplitude of 12 meters, and its spring constant is given to us as 108 kilograms per second squared. For the simple pendulum, that is going to be an object that will be given an angular displacement of 0.3 radians, and the acceleration due to gravity will be 2 meters per second squared, and the length of the pendulum is 648 meters. Shown above are 2 harmonic oscillators, the simple spring or the mass spring on the left and the simple pendulum on the right. For the first problem, for the spring, we're going to be solving for the motion formulas, and then we're going to solve the position, velocity, and acceleration formulas after 9 seconds has passed, and we're going to make sure we have units for that. And then for the pendulum, we're going to be doing the motion formulas for that as well, but since that is a rotational system, unlike the spring which was translational, here we will have angular position, instantaneous angular velocity, and instantaneous angular acceleration, and we'll calculate their values after 9 seconds. For a simple harmonic motion, in this particular scenario for the spring mass system, you're going to want to change your calculator over into radians for when we solve our trig functions. You do not want to have this in degrees. First thing we're going to want to do is we need to get to our angular frequency, omega, because that's part of all of our formulas for motion of a mass spring system. What we can start with first is solve for the period of our spring Ts, and that would be 2 pi times the square root of the mass divided by the spring's constant, which comes out to 2 pi times the square root of 3 kilograms divided by 108 kilograms per second squared. That comes out to 2 pi times 1/6 seconds. Now you could simplify that to pi over 3, but here's why we're just going to keep it as is. Frequency is simply 1 over the period, so that would just be 6 over 2 pi, or 3 over pi hertz. The angular frequency omega is 2 pi times the frequency, which what we have here is if we leave that 2 pi untouched from the period formula, we simply have 2 pi times 6 over 2 pi. The 2 pi's cancel out. If you had your 6 over 2 pi simplified as 3 over pi, well then 2 pi times 3 over pi, the pi's cancel out, and 2 times 3 still gets you 6. In the end, the angular frequency comes out to be 6 radians per second. Because that is in radians, that's why we need to make sure our calculator is in radians, since that is going to be inside our trigonometric functions. Now, when I mention the formulas of motion, essentially here's what I mean. For position, that is x of t, that equals the amplitude times cosine, angular frequency times time. And then the velocity equation would be negative omega times the angular times the amplitude times sine of the angular frequency times time. And acceleration, or a of t, would equal negative omega squared, where the negative sign is outside of the square so that you don't cancel it, multiplied by the amplitude, and then multiplied by cosine omega t. Or in other words, negative omega squared times x of t. What I mean by write the formulas is what's in the box. Simply replace the amplitude and the angular frequency with their values. So for example, for writing the formula for position, that would be x of t equals 12 cosine 6t. For velocity, we have negative omega times the amplitude. That would become negative 72. So v of t equals negative 72 sine of 6t. The acceleration, well, negative omega squared a, that would be negative 6 squared times 12. 6 times 6, 36, times 12 is 432, times negative 1 would be negative 432. Therefore, for this particular problem, you would write a of t equals negative 432 cosine 6 of t. And then the last part of this is actually just solving those equations, where we replace t with the amount of time that has passed. In our problem, that is written as 9 seconds. So x of 9 seconds, that equals 12 cosine of 54 radians. The 54 radians came from 6 multiplied by 9. 6 radians per second times 9 seconds equals 54 radians in our trigonometric function. For your calculators, just type 54 in those parentheses. So position after 9 seconds, that would come out to negative 9.952 meters. Velocity after 9 seconds will come out to positive 40.23 meters per second, and acceleration after 9 seconds would come out to positive 358.3 meters per second squared. For algebra-based physics, you're going to be given these equations, basically x of t, v of t, a of t, equaling a cosine omega t, negative omega a sine omega t, negative omega squared a cosine omega t, essentially all the things that are on the left, and you would just have to fill in the amplitudes and the omega frequency and the angular frequencies to write the equations, and then just solve them. For calculus-based physics, you'll be given the formula for the position x of t, and then you'll be expected to derive the velocity and the acceleration formulas from that initial position formula. For simple harmonic motion of a simple pendulum, again, you're going to want to have your calculator in radians, because we're still going to have our angular frequency. Now then, for this problem, what we're solving for is the period of the pendulum first, Tp, and that would be 2 pi times the square root of the length of our pendulum divided by the acceleration due to gravity. Now, that equals 2 pi times the square root of 648 meters divided by 2 meters per second squared. And therefore, that comes out to 2 pi times 18 seconds. Of course, you could leave that as 36 pi seconds, but if we're just a little bit lazy, we could just leave it as 2 pi times 18, because we know that that 2 pi is going to eventually cancel out. Well, frequency, firstly, is 1 over the period. Now, frequency being 1 over the period, in this case, period of pendulum, Tp, that becomes 1 over 2 pi, 18. And since period was in seconds, 1 over seconds is a hertz. And then angular frequency, omega, is 2 pi times the frequency, or 2 pi times 1 over 2 pi 18, where the 2 pi's cancel, and we're left with 1 over 18 radians per second. All right. Now, we have our angular frequency. For our equations of motion, here are the 3 equations of motion that we're going to be filling in. That would be angular displacement or angular position, theta t, equals our initial angular amplitude times cosine omega t. Now, the derivative, instantaneous angular velocity or angular velocity, that would be d theta t over dt, and that equals negative angular frequency times angular displacement or angular amplitude times sine of omega t. And then the next formula for instantaneous angular acceleration or angular acceleration, d2 theta of t dt2, which formally equals negative omega squared times angular displacement times cosine omega t, or in other words, negative omega squared theta of t, the angular displacement, the original formula. Again, for algebra-based physics, you'll be given those 3 equations to start out with. For calculus-based physics, you'll be given the angular displacement formula, and then you're expected to be able to derive the other 2 formulas. Now, for the part of our problem that's asking to write the formulas of motion, that is what is in the box, where we replace capital theta with our angular amplitude, and we replace the angular frequency with the value that we solved for. And for angular displacement, that becomes theta t equaling 0.3 cosine t over 18. For angular velocity, that becomes d theta t dt equals negative 1/60th sine t over 18. And then for angular acceleration, that becomes d theta t dt2 equals negative 1 over 1080 times cosine t over 18. For my algebra-based students, remember that cosine is in the numerator. That cosine of sine is in the numerator. It is never in the denominator for these problems here. Now then, solving each of those at the amount of time we're given, that would be again 9 seconds. Well, angular displacement after 9 seconds, theta 9 seconds, that comes out to positive 0.2633 radians. For angular velocity at 9 seconds, that comes out to negative 0.00799 radians per second. And angular acceleration comes out to negative 0.000813 radians per second squared. We're all remembering to include our units here. And the 1/2 in our parentheses for our cosine and sine functions, that was because we had 9 seconds divided by our angular frequency, 18. Well, or multiplied by 1/18. So 9 over 18 is just 1/2, or 0.5, and that's how we got all of our different values for this practice problem set. Of course, that covers everything for this. As always, likes and subscribes and comments are never necessary, but they are encouraged and they're fun to see. And so if you want, like the video, subscribe to the channel, and honestly leave a comment for any particular reason. In any case, hope to see you all in class, and as always, peace.